Hi, everyone. Our topic is SpatialNet, a self-adaptive and model-agnostic deep learning framework for spatially heterogeneous data. My name is Yiqun from University of Maryland. Co-authors are Xiaowei from University of Pittsburgh, Han and Xun from University of Iowa, Jia from Washington State University, Rahul and Prevan from University of Minnesota. Talking about spatial heterogeneity, it is a fundamental property of spatial data, which means the data distribution is different over space. To give an example in remote sensing, here we have the spectral characteristics of land covers from the satellite imagery being different at different locations, as we can see from this picture. Now, in the machine learning context, spatial heterogeneity violates the common, independent, and identical distribution assumption. Looking at this picture, we can see the data is generated by 4 different functions, phi1 to phi4. Here, each function phi is a mapping function from feature x to label y. And in this case, this data distribution cannot be approximated by one mathematical function or by one set of model parameters. The problem is very challenging because the spatial footprints of these different heterogeneous functions are often unknown in real applications. And also deep learning methods are data hungry, which means we cannot really split the entire space into very tiny pieces of regions and then learn a local model for each of the regions. In related work, spatial variability aware neural network shows that if you have data from 2 different locations with very different characteristics, then separating out the training for the 2 locations is actually better than training them together. However, SWAN requires the footprints of heterogeneity or data partitions to be known as an input. And also, it doesn't support parameter sharing across different partitions. Spatial ensemble can adaptively capture the footprints of heterogeneity. However, it is designed for binary classification and only supports up to 2 different functions or 2 different data partitions. A traditional approach is called geographically weighted regression, and this approach is mainly designed for linear regression and linear inference, and it cannot handle complex non-linear relationships in data, which is commonly addressed by deep learning models. Our proposed SpatialNet can handle all these different aspects. And this is our formal problem definition. In our inputs, we are given feature x and label y. And here, the function from x to y can be a mixture of different heterogeneous functions. We also need locations of data samples, as well as a user-selected deep learning architecture app. Our output is first a space partitioning where the function x to y in each partition is homogeneous. And also, we learn a corresponding heterogeneity-aware network architecture F prime, which is based on the input architecture F. The constraint is the resulting network size has to be bounded by a constant factor of the input network size. We have 2 major contributions. First, we propose a significance-guided GRL and collapse framework, which can simultaneously partition input data into homogeneous spatial groups and learn parameters for each group. We also have a strategy to share parameters across different spatial groups and to explicitly control the network size. First, let me introduce an overview of the sequence of space partitions that we use to separate out all the regions following different data generation functions. Now, in the growth space, we start with the entire space, and every time we do an equal area bipartitioning. And this is horizontal partitioning followed by vertical splits. We repeat this process until all regions following different heterogeneous functions have been separated out. And during the hunting of these regions following different functions, sometimes unnecessary splits can be introduced by using this predefined sequence of space partition. For example, here and here. And during the collapse phase, we will try to identify these adjacent partitions that shares the same function, and then gradually merge them back into the same partition. And one important decision in the process is to identify whether two partitions really share the same process, the same function, or different functions. And this is accomplished by a spatial heterogeneity test. And let me use one step from the growth phase as one example. So here we did a horizontal split, and let's call these two functions phi1 and phi2. The null hypothesis says these two functions are the same, whereas the alternative hypothesis says they are two different functions. And this is how we actually do the test. We take the network trained with data from the two different partitions, and then we explore two different scenarios. In the first scenario, we say, okay, the model, the two functions are the same, so we can train the network. We can continue to train the network using the combined data from the two partitions. And in the second scenario, we say the functions are actually different. So we create two different branches where each branch is trained by the corresponding data from the individual partition. And after we finish the training, we evaluate the loss using validation data from the two partitions, and we calculate the difference, perform our significance testing. Specifically here, we use a dependent t-test. More details can be found in the paper. If the improvement from the split scenario is significant, then we implement the two new partitions as well as the two new branches in the network architecture. And of course, when we create the new branches, we don't really want to create a complete copy of the entire deep network architecture. And instead, every time when we do a partition, we keep a proportion of the layers shared by the two different partitions. And then we create new branches using the rest of the layers. And similarly, when we go to smaller partitions, we keep a proportion of the layers in the existing branch shared across the new branches, and then we construct these new smaller branches using the rest of the layers. And as we can see in this process, the smaller branches, the smaller partitions only need to learn a smaller set of private parameters. And to make this a bit more formal and to have more guarantee, we introduce an exponential reduction tree. So suppose this is our initial total L number of layers. And every time when we do the split, we take the last 1/β proportion of layers and we create new partitions based on that. And as we go to smaller partitions, we take the 1/β proportion of the current branch and we create new branches based on that. So we repeat this process. Using this sequence, we can guarantee that the total number of layers in the resulting network is bounded by this quantity. And to give one example, if we set beta equals to 2 and we allow 64 different partitions, different branches, then the network size is actually bounded by 4 times the original network size. In our experiment, we tried land cover classification on 2 different data sets in Minnesota and California. And here we are trying to infer the land cover classes using Sentinel-2 satellite imagery. We tried 2 different base network architectures. First is a fully connected neural network, and the other is a convolutional neural net. And here I'm showing the F1 scores for the California dataset as one example. The red boxes shows the fully connected network architecture. The left one is the base network, the right one is the spatial net version. of the fully connected network. And the green boxes shows the UNet result. And again, the one on the left is the base UNet. The one on the right is the spatial net version of the UNet. Looking at the numbers, we can see by considering the spatial heterogeneity, we can substantially improve the model prediction performance. And here I'm giving a visual comparison between the results. On the very right, we have the ground truth reference. Again, by comparing the deep network, the base network, and the spatial net, we can see the spatial net can greatly improve the prediction performance. We also carried out a synthetic experiment. On the left, our data in the space are generated by 4 different functions. And on the right, we are showing the footprints automatically captured by our spatial net. And finally, to conclude, in this work, we propose a spatial net to handle spatial heterogeneity, which can be broadly applied on different network architectures. And also, we propose an exponential reduction tree strategy to share the parameters and control network size. Our experiments on both real-world and synthetic dataset shows the spatial net can substantially improve model performance, and it is effective in capturing footprints of different heterogeneous functions. In our future work, we want to generalize this work to more machine learning methods, and we want to generalize it to capture irregular shaped footprints. And thank you. Please let me know if you have any questions.